All right, line A6, learning task 2, features of SCRs, or the silicon controlled rectifier. SCRs are a very old part of our thyristor family. Thyristor means that they're all based around this material called thyrite, which you may have heard about before. Thyrite has an interesting property in the fact that it's got an extremely high resistance at low voltages, but a low resistance at high voltage. In other words, it's going to go and kind of break over. And so we started with thyristors that years and years ago were just kind of used as simple things that could turn stuff on. The voltage gets high enough, stuff turns on. We're going to find out about some of those devices later on once we investigate diacs and triacs and stuff like that. But it's the whole family of semiconductors that we can turn on and off are all kind of classed as being part of this thyristor family. They are unidirectional. Just like our diodes, they are going to only allow current through in one direction, but they're going to go and have 3 terminals. And in a lot of ways, we are going to go and see these things as being controlled diodes. We call these things the silicon controlled rectifier. It does have this one terminal down over here called the gate, which is going to go and allow us to put this thing into conduction, and then it is going to go and stay in conduction until it's going to reach a certain other value of current, which is going to be its dropout value of current. One of the really interesting things about these compared to what we've looked at so far, we've looked at unidirectional switching before when we were looking at our FETs just in the previous learning task, as well as when we were looking at our BJTs, but all of those need a constant supply to either the base, in the case of a BJT, or to the gate, in the case of a FET. These ones only need to go and have a pulse, and that's really a huge thing to us because we don't have to have a maintained signal there. We just give this thing a blip, and that signal is going to put it into conduction. Because they only use a small amount of time, therefore they're going to have a small amount of control power that's going to be dissipated as well, because it's only happening for a couple seconds that we're going to go and see this pulse over here. Therefore, it's not going to be a long-term, large kilowatt-hour expenditure of energy that we're going to go and have. They do have a difference, though, from our FETs and our BJTs. Our FETs and our BJTs, we can use them as analog devices, where we can go and depending on how much current we place to them or how hard we bias the gate on our FETs, we're able to go and adjust how much they go and conduct. That means that they're going to be analog because we can go all the way from, a value of 0 to infinity, depending upon the size. But theoretically, we can go and change any values inside of a given range. These ones over here are going to be bistable. They're either going to be 0, off, or they're going to be instantly fully on. So it's got only 2 different states that it can be in. Our leads are going to be very similar to what we had off of our diodes. Anode, cathode are both going to be identified the same way. Our anode is going to go and be that little triangle. Our cathode is going to go and be that little line, and then we're just going to go and connect that gate terminal over to the cathode itself. They're going to come in a variety of different configurations. What they're showing over here is they're showing a large high current SCR, the type of thing that you're going to use when you're doing a lot of high power rectification, DC buses for industrial plants, etc. Other times they're going to go and have smaller cases that are going to go and look, something similar to these ones over here, the tab type, which are going to be a lot smaller, only a couple of mil across in a lot of cases. The more current that we have to go and switch with these things, the larger of a case that we are going to go to. And in some cases, part of the actual case itself is going to go and be a part of the switching components. This over here, this anode, is designed as a stud type. And what you're going to do is you're going to take this thing, you're going to thread this whole thing into a heat sink so you can dissipate heat away from the junction, prevent it from failing. But you are going to have to go and make that entire heat sink that it's threading into part of your anode or your positive system. These are made up out of 4 layers of semiconductor device. We have got our PN, and that means that in between all of these, we are going to once again have individual small depletion regions. So we're going to have one there, etc., all the way through. And the way that we are going to put these things into conduction is we're just going to go and give an initial little blip of current to my gate to cathode that I'm going to go and have. If you take a look at the gate to cathode over here, you can see that the gate is on the P type of material and the cathode is going to be an N type of material. If I were to just ignore everything up at the top over here and look at just that bottom section, it looks like a regular diode. And to put a regular diode into conduction, all you do is put a positive and a negative real quick onto that thing, blip, blip, and it's going to go put it into conduction. Remember how we use that analogy of the fact that you can't blow up one side of a balloon? Well, as soon as you go and put this one into forward bias, you're going to go and at the same time be putting more holes into this P type of material, which is going to go and shrink down this one. And if this one is shrinking down, that in turn is going to cascade over and shrink down this depletion region over here. And what happens is that end to end, then all of a sudden we are going to, that's the wrong direction, end to end, all of a sudden we are going to go and have current flow that can go through from our cathode, or more negative point, all the way over to our anode. They're going to have a bunch of ratings that are going to be used for selection. Stuff that we're going to be caring about are going to be the amount of current that this thing is going to be able to go and carry, continuous current, or anode forward current as it's sometimes referred to, maximum continuous RMS current rating. And if you go over that, you're going to go and destroy it. We've got a couple of other things that are going to be like repetitive reverse blocking and forward blocking voltage, and then holding current, which is going to be a really important one as well. It's going to be a minimum current required to sustain conduction. It's going to be in the, the milliamps in a lot of cases, and if we fall below that value, all of a sudden we are going to go and lose conduction. The thing is going to go and shut off because we just won't have enough currents traveling through this pathway over here to go and maintain these depletion regions as being pushed all the way back down. If we fall below that certain amount, these depletion regions can rebuild. Remember, we don't have signal continuously on our gate, but these depletion regions could rebuild and shut off our current flow. So we're going to be looking very carefully at the amount of holding current. If they fall below that, they shut off. We're going to also have these two, which are going to be looked at together, VGT and IGT. It's going to be the voltage to the gate and the current of the gate. We need to go and figure that out, put those two together, multiply them. You're going to find out the total amount of power, the instantaneous power that you're going to have at the gate. And remember, it's just going to be a little pulse. But it does have to be a proper value of voltage and of current. And looking at your voltages, once again, you are going to go and see that all that you really need to do is put this PN junction into conduction. So it's not going to be very high of a voltage that you're going to need on the gate. You just need to overcome that barrier, which is usually going to be around the 0.7 of a volt mark. This one, next one down over here, DVDT, is going to be a rate of voltage rise which will turn the SCR on without a gate signal. And sometimes you're actually going to go and see this thing as DVDT with a Greek letter D, which is the letter or the symbol that we call delta. This just means change in voltage over top of change in time. You should have seen this already back in second year. It should be familiar to you, but it's just saying, look, if we have a really rapid change in voltage over top of a short amount of time, we can put some of our devices, we can basically just shock them into conduction. And what's happened is because we go to a super high value of voltage right over here and a super, in the opposite direction, negative value of voltage in this one here, what happens is we just all of a sudden flood this section over here with holes, or with electrons. We flood this top section, let me just remove that, with holes over here. And it can be enough that it can just cascade over into here. This one can cascade over into here. And if these ones flooded fast enough to cascade here, these ones flooded fast enough, the two of them together will be able to overcome this one, and all of a sudden the whole thing just goes right into conduction. We want to be very careful. Therefore, we have to be careful about the frequencies that we're going to go and put them on. Obviously, the greater the frequency, the shorter the amount of time that we are going to go and have associated with them. So watch your frequency ratings. Taking a look at one over here, this is just a spec sheet that they're going to go and have on, or a simplified spec sheet. What I would be very, very much interested in if I was picking this out for a rectifier for any of my industrial applications is I'm going to go and take a look at my voltage on the gate, very small, 2 volts, and current, 30 milliamps. So I'm going to go and build a control circuit that is not going to deliver more than 30 milliamps and not going to deliver more than 2 volts. Just sublift it. Basically, you take a look at it, you could run this or gate this thing off of a battery, And then I'm going to go and take a look at what the maximum forward voltage that I'm going to go and have, which is going to go and be 600 volts that I can block, so I can turn 600 volts on and off with this one. And then my total amount of current that I can go and carry for is 25 amps. Take a look at your actual connections over here. You're going to go and see that you're going to go and have your anode over here, your cathode over here, which means that once again, if this is going to be attached to any sort of a heat sink, an industrial heat sink, that industrial heat sink is actually going to go and be charged. It's going to be at a positive value of voltage for this thing to operate. Be very careful around industrial equipment. If you open something up and you see heat sink, I know a lot of heat sinks are connected over to ground, but you have to be very careful about which ones you touch. If it's isolated and inside of a cage or like inside of a component casing, there's a good chance that that thing is actually live. Don't assume that these are all going to be dead types of things. Last of all, common case styles, pile of different cases that these things can come in. I wouldn't worry too much about knowing what these case styles are. To be honest, anytime that you're going to be looking for one of these for replacement, you're going to start with the manufacturer's part number. That's going to go and tell you the case styles. The other reason that I don't want to spend a lot of time off of this one over here is because the sizing that they're showing over here is very, very misleading. It looks like the TO92 is, pretty much the same size as our TO64 or some of our big, 220s and 48s and stuff like that. In reality, we're looking at size differences that are, like this type of idea. The TO92 is going to be a very tiny little one, and some of our larger stud mount ones that we are going to go and have, like the 48 over here, are going to be, comparably much, much larger. All right, that's it for our intro to these. We will move on to the actual operation.